Hello, everyone. My name is Chu Shibai. I'm a PhD student from University of California, Irvine. Today, I present our work, Maliva, using machine learning to rewrite visualization queries under time constraints. This work was done jointly with my colleague, Sadim Alsudayes, Professor Chen Li, and Professor Shuang Zhang. In today's data-driven world, visualization applications are extremely popular for people to quickly discover insights into their data and make timely decisions, such as Power BI, Tableau, SuperSight, and many more. Most visualization systems follow a typical three-tier architecture of front-end, a middleware, and a database. The users interact with the front-end and send visualization requests to the middleware. The middleware translates the visualization request into a database query, and the database executes the query and returns the result. In this visualization architecture, the response time is critical, and some research work has shown that if the response time goes beyond 500 milliseconds, people may lose the context of the analysis. And in many cases, databases can now serve the queries within the time constraint. For example, in our experiment, this is a real query formulated by the visualization frontend to show a geospatial distribution of tweets that are filtered by conditions on the textual, temporal, and spatial dimensions. We ran this query against a Postgres database that had 100 million tweets, and the query took 8.8 seconds to finish. Interestingly, if we rewrite the original query by adding a hint that asks the database to use the B-tree index on the temporal dimension, together with the inverted index on the textual dimension, the new rewritten query only took 300 milliseconds to finish, which is significantly faster than the original query. The original query was very slow because of the physical plan was not efficient. The original query plan used the R-tree index on the spatial dimension, together with the inverted index on the textual dimension. And it turned out that the R-tree index scan was the bottleneck, which took more than 8 seconds. And a deeper look into the plan shows that the database failed to choose an efficient plan because of its bad estimation on the selectivity of the spatial filter. It underestimated the number of rows by 240 times. Unfortunately, this problem is prevalent in our experiment, where we visualized tweets data on a Postgres database. Among the 600 queries we analyzed that had at least one plan that can finish within 500 milliseconds, Postgres missed the deadline for almost 45% of queries. And if we rewrite them smartly, we can make all of them meet the deadline. One natural question is there are many high accuracy estimators in the literature that can help on this problem. Why a database cannot use them directly? One reason is that those high accuracy estimators usually have a high cost. The cost can go from 10 milliseconds up to even 100 milliseconds for estimating only one query plan. And databases are designed for general purpose. For low latency transaction queries, where the query time is only a few milliseconds, it can be unacceptable for a database to take tens of milliseconds for query planning. However, this opens up a new opportunity for us to develop a middleware solution. Since we know the time constraint is 500 milliseconds, we can utilize the expensive estimators to help the database to generate a good plan. For example, we can spend 150 milliseconds on the estimators to evaluate different plans' query time and find a viable plan. That the viable plan only runs for 300 milliseconds. Then we still meet the 500 milliseconds deadline. To this end, we want to solve the following problem. Given the visualization query, we consider a set of rewriting options, such as adding hints, and we enumerate different rewritten queries carefully. Ask the query time estimator to estimate their query time. We want to find one rewritten query such that the total response time is less than a given time constraint. The total response time should include both the planning time and the query execution time. There are a few challenges to solve this problem. First, apparently, brute forcefully enumerating all possible rewriting options are too expensive. Second, there are uncertainties such as the QTE can have errors and the database may ignore the hint in the rewritten query. To address the challenges, we propose Maliva. It stands for Machine Learning for Interactive Visualization. Maliva is a middleware solution. For a given visualization request, the query writer explores different rewritten queries carefully, asks the QTE to estimate the query time, and eventually chooses one rewritten query to send to the backend database. The goal of the query writer is to maximize the chance that the total response time can meet a predefined time constraint. How does query writer work? We now follow an example to explain the main idea. The query writer works like an agent. For example, the left bottom query is the running example we used. Consider adding different hints of using different combinations of indexes as the rewriting options to this query. We have 8 different rewritten queries as shown at the right bottom. Suppose we know the following information as shown on the top of the agent. We know the 8 possible rewritten queries RQ0 to RQ7. For each RQ, we know roughly how much time it takes for the QTE to estimate its query time. Based on previous experiences, the agent may choose to export RQ1 due to its low estimation cost. And it turns out QTE takes 30 milliseconds to estimate RQ1's query time. The estimated query time for RQ1 is 1.3 seconds. We take down the new information and also update the cost for other RQs, since estimating different RQs may have overlapped cost. Given the 500 milliseconds deadline, we haven't found a viable RQ yet, so we continue. Given the information from estimating RQ1, now the agent may decide to estimate RQ5 next. Now we spend another 60 milliseconds on the QTE, and we know RQ5's query time is roughly 1 second. A little bit better, but still not fast enough. Fortunately, we still have some time to explore more RQs. The agent decides to explore RQ7. After spending another 60 milliseconds, it turns out RQ7 is roughly 300 milliseconds query time. So if we run RQ7, we can meet the deadline. As we can see in the example, to find a viable rewritten query, the query writer needs to make a sequence of decisions. It explores one rewritten query, spends some time on estimating its query time, then based on the new information, it chooses a new one to explore, and so on and so forth, until it either finds a viable query or it runs out of time and chooses the best one it knows so far. Then the question becomes, how does query writer agent learn those previous experiences and make those sequence of decisions wisely? We model this problem as a Markov decision process. As we can see in the example, in the model, the query writer is agent, the QTE and the database together are the environment. The agent iteratively interacts with the environment. The actions are either estimating a rewritten query or running it against the database. Then the time spent on either the QTE or the database can be the reward to the agent, and the output information will be used to update the state of the agent, which stores the knowledge the agent has so far. With this model, we can use reinforcement learning techniques to train the agent on historical workloads, such that for new queries, the agent can make good decisions. In the paper, we have all different kinds of details of the definitions and the learning algorithm. We encourage you to check that in the paper. To evaluate the effectiveness of Maliva framework, when conducted experiments on Twitter, TBCH, and NYC taxi datasets, we use PostgreSQL and a commercial database. This figure shows the advantage of using Maliva to rewrite queries on the Twitter dataset with 500 milliseconds as the time constraint. The x-axis is the viable query percentage generated by different approaches. The higher, the better. Viable means the generated query plan was less than 500 milliseconds time constraint. The base one was the original query plan generated by Postgres, which had only 1% of queries viable. A state-of-the-art approach increased that to 18%, and the Maliva approach increased that to more than 74%. To summarize, in this paper, we solved the problem of writing visualization queries under time constraints. Our solution, Maliva, is a machine learning-powered middleware rewriting framework. It uses high accuracy and expensive QTEs. We modeled the rewriting process as a Markov decision process, use reinforcement learning to train the agent, such that it explores different rewriting options carefully. In the paper, we also extended to support approximation rewriting options. This concludes my presentation. Thank you for your attention.